Very good. I would say we can start with the second part of the lecture on the S-matrix bootstrap. And it's a pleasure to have Andrea Guerrieri that will give this lecture. Please.
Okay. Thank you so much for the invitation. Okay, thanks also to Lucia for the amazing talk. I don't have to do almost anything, so it's really easy like this. So, in the second part, I will basically generalize what Lucia have already told in 2 dimensions about the bootstrap setup. Now, to do it a little, I need to go a little bit into the details of unitarity, crossing, and so on. So I will go a little bit into the details. So let me start. So it's S-matrix bootstrap for IRD. Okay. So the first part of the talk will be from d equals 2 to d greater than 2. It's already not trivial. And then in the second part, I will jump right away to what is it, I think, related to one of the questions of the people here. What are the observables that we want to bound? Okay, and in the last years, in higher dimensions, we understood that what is good to bound are effective field theories. So I will talk about effective field theory bootstrap. Okay? And in particular, I will focus on one effective field theory that I like, which is like 10-dimensional quantum gravity. So D equals 10, quantum gravity. And then, okay, I will draw some conclusions at the end, with some dreams. What is the final goal of this program? Okay? Okay. So let me start from one of the last things that Lucia said about the fact that the space of S matrices, we do expect to have a very complicated structure, especially in higher dimensions, right? So we do expect to have some very funny shape, where maybe in 2 dimensions we can have at these cusps, at these tips we can have integrable theories, but in higher dimensions we don't have them anymore, okay? So somehow it will be clear that what we really do is really find a space of consistent theories. Okay, and if we were able to impose all the infinite constraints that come from unitarity, eventually we would find the real boundary of this space. Okay, the shape of this space, as you already heard, is determined by crossing, okay, unitarity, and analyticity. And what I will do now is that go over all of them and generalize them to higher dimensions. But then, what I will do in the second part of the talk is to add to these 3 very general principles the low energy behavior. In the effective field theory, which sometimes is also connected to soft theorems. Okay, so it's something that people from celestial amplitude might like. So it's related to soft theorems, sometimes. Okay, so let me start, okay? So let me tell you a little bit, let me start from some formula you see already said. So let me define the S matrix, okay? In the textbook is usually defined as the overlap between some out state a beta and some in state alpha, okay? And the S matrix is the unitary operator that changes basis. So I can write here beta in, there is some operator S dagger, alpha in, okay? Good. And this operator is unitary, which means this, okay? That in 2 dimensions we could use directly. Now I'm telling this because usually in higher dimensions, what we really consider is the scattering amplitude, not the S matrix itself. So what we usually consider is that we split this operator S into an identity where the particles fly off without interacting with each other, plus I, T, a matrix which is the scattering amplitude. Okay? Now you see these are operators. Okay? So what we usually do is that, we compute them, bracketing them with some states. Okay? So if we use eigenstates of the momentum operator, right? So effectively, this S becomes a distribution, okay, in general, that will depend on the four momenta. So let me draw a picture. So we have this scattering experiment where we throw against each other particle momenta P1, P2, and we get in the final state particle in the future with the momentum P3, P4. Okay? This function will depend on this momenta. Okay? Let me write it more explicitly. In generic dimension, okay, so in any dimension, this will be some conventional factor 2 pi to 2d minus 1. Then there will be the normalization of the delta function, which is energy of the particle 1, energy of particle 2. And then there is this disconnected contribution that corresponds to the identity operators, okay, where the particles flies off without interacting. So there will be some delta d minus 1, P1 minus P3, delta d minus 1, P2 minus P4, plus the process will exchange particle 3 and 4, right? So this means that the particle 1, let me call this 4, let me call this 3. Just means the particle 1 conserves its momentum. It becomes momentum P3. Okay? Plus I, 2 pi d, then there is the momentum conservation, P1 plus P2 minus P3 minus P4, where these are 4 momenta without the R on top. And then there is this function, which is the scattering amplitude, T of S and T, okay, that are defined as, let me remind you, as P1 plus P2 square, and T is P1 minus P3 square. And the claim is that this function is, is a function, actually. It's not a distribution. Okay? Too much errors. Thanks. Okay? So the claim is that this is a distribution in general, but this is a function. All right? Okay. So now, let me write down this Mandelstam invariance in a specific frame, which is quite useful, which is the center of mass frame. Okay? So in the center of mass frame, it's very nice. So it's defined by setting P1 plus P2 equal to 0, which is also equal to P3 plus P4. This is how it's defined. And since the S and T variables are invariants under Lorentz transformation, this boost, it won't change the physical meaning of those variables. But if we go to this frame, then the process, the 2-to-2 processes really simplifies it a lot. Okay? The two particles now have momenta that are collinear, so this will be P1, this will be P2, and then P3, P4. And then here you see that in 2 dimensions, right, there is no angle theta, because the particles are constrained to move on a line. But in higher dimensions, we have also this variable here. So instead of having one single variable, as you see I wrote in the special relations, right, with the special relation in the S-plane, now we have 2 variables, okay? The center of mass energy and the angle theta. And they are related to S, let me remind you, by S is equal to 4 g squared of the particle which is the A, and T is minus 4p squared sin square of theta over 2, and U it's just, you can just imagine with some algebra, squitta, and this is positive, and these 2 are negative, okay, for physical processes. when I say dimensions, I mean d minus 1 plus 1. So when I say two dimensions, so when I say two dimensions, I mean 1 plus 1. My picture is not a space-time picture. My picture is a space picture. So these are three momenta. So the black hole is 2D space, but in general, I mean, the 2-2 scattering is planar because you can use.
It's okay. It's just that you said that in 2 dimensions you have an angle theta, and I just want to say.
You don't have an angle theta.
You said you don't.
You don't have an angle theta.
Okay. So I thought you meant 2 plus 1.
Ah, no, sorry. No. Okay. No, I said, okay, yeah. They would be collinear.
Sorry, this is related to the fact that in 2 dimensions we could always choose u equals to 0.
Yes, the fact that u equals to 0 is a consequence of this. Exactly. Now you have to keep it. Yeah. And this is quite a complication. It's not, yeah. Okay. Then, of course, in general, let me say that in general, S plus T plus U is equal to sum of the masses of the particle that, well, can be 4m squared or can be also equal 0, as I will consider scattering of massless particles later. Okay? And because of this relation, well, T also can vary from 0 to 4m squared minus S. Okay, so now that we know the kinematics, the first properties that I want to address is crossing. Right? So you see, crossing is just the fact that if I take this amplitude as a function of S and T, for instance, must be equal to the function of T and S. What I mean for this? What I really mean for this is an analytic continuation, in the sense that in this entry there is like a variable that is positive, in this entry is a variable that is negative. And now what I'm saying is that this S can be moved to negative values, okay? And this that I call T, this negative value, and this second entry can be moved to positive values, and this function doesn't change. Okay, so it's really permutation invariance, in other words. It's really an analytic continuation. Well, it will be clear in a moment why it's an analytic continuation. Because you don't want to, you will have, if you move on a path that is real, you will hit singularities. Okay, so you really need to go to the complex plane. Okay. Now, unitarity. Sorry?
So this equation works when u is equal to 0 or it is any u?
This is for any u because, well, u it's just 4 minus S minus T. So it will be negative. Yeah, thanks. Thanks. Okay. So, okay, so far so good. This is just a simple, it's a, right, it's very simple extensions of 2 dimensions, right? Here crossing, it's a little bit more complicated because U depends in this way on S and T. Okay, so unitarity. Okay, so unitarity, if I split down the S metric as 1 plus IT, can be written in this way. It becomes the 2 times the imaginary part of T, which is equal to T hat T dagger. Okay? And this is why reason, for instance, there is a T develops an imaginary part, why there is a branch cut. Okay? Okay. And now what we do is just that we insert a completeness relation, right? We insert the identity is equal to some measure that will depend on momenta, K1, K2, and we insert a complete basis of states that starts with the two particle states, but then there will be multi-particles contribution, right? Multi-particle states. And if we insert this completeness relation inside the unitarity and we evaluate this operator on momentum eigenstates, okay, this relation becomes that the 2 times the imaginary part of t, that now will be a function not just of S but S and t, okay, big T, is morally equal by an integral, okay? By an integral of, well, you insert this complete relation inside, right? So you have t on one side and t dagger on the other side. So we'll have t, which is a function of S and some t prime that is function of t. There is a t star on the other side. This is some t second as a function of t. Okay? And here you will have some double integral on dt prime, dt second, with some kernel that I won't write, because it's not what I'm going to talk about. But what I want to say is that when you express in a basis of function, this unitary relation really becomes the imaginary part of the product of the amplitude with the star, with some kernel, which is what we are going to diagonalize soon. But this is the statement of unitarity, plus, of course, multi-particle contribution. Okay? Now, to diagonalize this kernel, what we will do, and will be useful later, we'll introduce partial waves. Okay? And the reason to introduce this basis, these new spaces, is to diagonalize this kernel. Okay? To diagonalize this integral. Now, partial waves are defined in this way. We define FL of S, which is equal to some normalization factor that depends on the dimension, the integral from -1 to 1 in the Z, where Z is the cosine theta. Okay? Here there is some measure that will be important in when we go to 10 dimension, d minus 4 divided by 2. Then there are the d-dimensional partial wave, which are just Legendre polynomials in d equals 4. And then we have t of S and t of Z. All right? Okay. So this projection is useful. And let's say that there is also an inverse. So there will be an inverse for this projection. And the inverse is just the fact that t of S and t, can be written as the sum of spins with some normalization factor, again, that depends on the spin and the dimension d, okay, of FL of S, and the dependence on the angle is contained in the argument of the partial waves. So you have PL d of Z, which is a function of t, if you want. Okay? And now let me just say one consequence of crossing on this sum, right? Is that crossing, what it does, exchange effectively cos theta to minus cos theta, right? Because we rotate by pi. Right, we change cos theta to minus cos theta, and if this function must be crossing invariant, since the partial wave, if I put a minus sign here, so -1 to the L is equal to PLD of Z. Okay, they are even well, they have this property, all right, this parity property. Then it means that for identical particles, this sum is just done on the even spins. Right? Okay. Now let me write here. So we introduce this basis, okay? And you can perform. you can insert this basis into this integral, and then what you would, if you do this computation, what you will find. So let me erase here. What you will find is that this relation diagonalizes for any spin. In particular, decomposes infinite relation of this form that 2 times the imaginary part of the partial wave, FL of S, is equal to some factor, which is in general S minus 4m squared to d minus 3 divided by 2. And here there is like the energy. The absolute value square of the partial wave, okay? Plus positive contribution. D equals 3, it's it just goes away. Just goes away. In 2 dimensions, you will get a 1 over square root of S minus 4. No. Exactly. All right? So this is the unitarity. Okay? This relation must hold for any spin, even, and for any S, bigger than 4m squared. Any physical S. Right? Now, since these are positive contributions that come from the multi-particle states, we can neglect them and get the weaker conditions, right? We can just neglect them and get the weaker condition that, this becomes an inequality if neglect them, all right? And this inequality can be actually wrote in a similar fashion as in 2 dimensions, can be wrote as a probability conservation as in 2 dimensions. So you can check that if I introduce some partial S matrices for any spin that I can also write as a phases, right? E to the 2i delta ls, where this delta ls must not be real, can be complex in general. And this can be written as 1 plus I, and we put this, this factor again in front. Square root of S. If you introduce this function in this way, then this inequality condition really becomes the condition that SL of S must be less or equal than 1. And this is the unitarity that Lucia was imposing in 2 dimensions, right? So in higher dimensions, it's just become a statement about, it's just like if you have infinite copies of 1-dimensional S matrices, okay? You have infinite of them that are related by crossing in a complicated way. All right. Now let me make a plot now. So what are we saying? We are saying that for any fixed S, this function must be contained in this circle. Okay, this is the function SL. For delta equal to 0, right? For delta L equals to 0, you have the free theory. And then if you are on the boundary of this disk, where SL of S is equal to 1, you have no particle production. No PP. And if you are inside, we do expect the physical theories in general will be inside, a little bit inside. Okay? Let me mention that this is not just, this fact can be proven actually because there is the so-called Axe theorem. There is the Axe theorem that says that if you have crossing in higher dimension, then you must have particle production. Okay? Huh? Unless? Unless the theory is free. Exactly. Thanks. All right. So, okay, let me move to the last. So this I will keep it, this I will erase it. This means that there cannot be any theory that for any physical value of S can be on the boundary. Exactly. Well, the symmetric, from a Lagrangian perspective, right, you can have these things, but from the symmetric point of view, free theory is just all partial waves equal to 1. Yeah. Okay. Okay. So the last property that I'm going to mention is analyticity, so how it changes when we go to higher dimensions. Okay. But please, if you have a question, you can interrupt him. If it's too basic, you can tell me. I can. Right. Yes. So if you if you combine these FLS that are constructed in that way, right? So if you project the amplitude, you obtain these FLs, and you write them in this way, that this inequality becomes this inequality. So the fact that 2 part imaginary part is bigger than the absolute value square, it means that this is less or equal than 1.
And how is SL defined? What is delta? SL.
So SL is defined in this way, which is defined in this way. So this, so SL, okay, let's forget this. So I define SL of S as 1 plus I FL.
The question probably is how it's related to the scattering. Why do you call it S?
Yeah, can I think of it as a partial wave transform of the whole X matrix with the 1?
Yes, okay, good, thanks. So you can obtain it if you start directly from eigenstates of the angular momentum and total momentum. So if you start, because here I started from momentum eigenstates, right? The momentum of the particle is not conserved. What is conserved is total angular momentum. So if I go to the right basis from the beginning, what you will have is that if you scatter particles with some fixed energy, a fixed angular momentum, right, the overlap between these two states can be written in this way.
So I think with this partial wave decomposition, you have repackaged the information of T inside the L, I guess, no?
Exactly.
So, and then you have obtained something similar to what Lucia was talking about before, not just a function of S, but infinitely many of them.
Infinitely many of them, exactly. So the fact that we have an angle, theta, translates into infinita. Is it?
Can you repeat the theorem where it comes from? Because it just falls from the sky, so I don't understand. At some point you said crossing implies.
Right. Right. So what I wanted just to stress is that unlike in 2 dimensions, where you can have integrable theories, in higher dimensions there is a theorem that prevents, in principle, to even think about constructing an integrable theory, apart the complications that you would encounter. But there is a theorem that says that if you have crossing, and as Alessandro was saying, the theory is non-trivial, then you must have particle production. There is no way out. Yes, there is a diagrammatic intuition. Okay, we can discuss later. I mean, it's a bit. It's not that simple.
Maybe I make a quick comment. At some point, Lucia was saying that you can take these lines and move them because they have all these symmetries. They make things integral, but they can decompose the young buster, right? You can decompose the scattering this way. So that is particularly easy to see that doesn't work in 3 dimensions.
But this, it's beautiful. Can be really proven from axiomatic field theory and uses only the proven analyticity properties. So it's striking, this theorem. Okay. Okay, so what I wanted to do now is just mention a little bit analyticity, and then I will move to an application and talk about a little bit about physics, which will be more fun, I hope. So analyticity in higher dimensions, of course, it's very hard in higher dimensions. What I will do is the following. So imagine that we fix S, right? Sorry, imagine we fix T. Sorry. We fix T. And then what we expect is that as in two dimensions, we'll have like a branch point singularity starting at 4m squared. All right? But then now the left cut, it's not fixed at 0, because that's two dimension, but it will be a moving cut. It will start at minus t. Right? And this minus t is just the starting point of the U-channel physical process. All right? Now about this t, this fixed t, okay, so this fixed t, in the complex t plane, there is some potato region where you can fix it inside and prove that for any fixed t inside some region, the scattering amplitude is really analytic apart from branch point singularities that are located on the real axis. Right? This can be proven. What I will assume, and what we will usually assume, is a little bit more, that we can extend this domain of analyticity to any t, avoiding the t-channel singularities, because also in the t-plane there will be at some point cuts. So if we are away from the cuts in the t-plane, the claim is that in the S-plane you still have some structure of this kind. All right? It's what is called the maximal analyticity. Right? Are there questions about analyticity? Okay. Okay.
Is this like an assumption but not proven?
Maximal analyticity, yeah, it's not proven. It's an assumption. Yeah, in the whole plane, I avoid the singularities. Yeah, I mean, simple poles are trivial in the sense that you can add them if you stay away from the bound state poles. So. Right, of course. I mean, it would be a moving pole, of course, and you have to avoid that singularity. It would be a line. Yeah. 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 But those are fine. It's not. Okay. No, the real problem are general Landau singularities that come from multi-loop diagrams. That's the real deal. Okay. Okay. So I think this is enough for the generalization from 2 to higher dimensions. So now we'll move right away to effective field theory bootstrap, which is really the new ingredient, okay, in all these games. So Coleman-Thun singularities in higher dimensions do not give rise to double poles. They give rise to logarithmic singularities. So double poles are a feature of 2 dimensions. All right. Okay, so let me consider d equals 10, not d equals 4. Let's go right away to d equals 10. And let's consider massless particles. Let's send m that goes to 0. Then you see all the formulas here, I mean, they can just easily analytically continue to m that goes to 0. What is trickier is this analyticity structure. But you see, these branch cuts will just start at 0 if we move m squared to 0. What we lose is that we lose any rigorous arguments in the sense that there is, I mean, people have never proved the existence of any such region in the T-plane when you consider massless particles. So we will buy this assumption and we will generalize it to massless particles. Okay?
On top of like the mathematical aspect of this assumption, there's the physical aspect that you can have the distribution of soft particles.
Right.
That it shows up in any calculation you do. So how does
Right. Right. So that is usually related to long-range interactions. Okay, of course. Now, what we consider in general massless particles, like, for instance, in 4 dimensions, we would like to scatter massless pions. And massless pions, they have a short-range interaction because the theory confines anyway. There is lambda QCD. So in that case, the S matrix can be defined, the massless S matrix, and there is no such issue as infrared singularities. I'm talking about gravity, I'm talking about gravity in D10. So in D equals 10, yes, still long range, but the angular integration, when you project into partial waves, has a 1 minus z square to some power. That's cosine theta. And that would cancel the divergence when you go to theta equal to 0. Okay? So if you consider gravity in d greater or equal than 5, actually, still define S matrix without worrying about these infrared singularities. It's really a problem of going to d equals to 4 and lower dimensions, of course. Okay? Right. Right. I mean, there are arguments that in d greater or equal than 5, you can construct such states. So, no, I mean, I remember some papers by Giddings and Port, for instance, where they have a lot of arguments about this, but it's, I mean, there is little that can be proven rigorous. So it's just based on physical intuition. Okay. Okay, so what I would like to consider is the Graviton scattering. Which falls off of the paradigm of scalar particles, right? But with maximal supersymmetry, maximal SUSY, I can just consider scattering of the scalar superpartners. Because of maximal SUSY, you can consider actually the scattering of any massless particles in the supermultiplet, okay, the massless supermultiplet. And this will be given by just an R to the 4 factor that depends on the polarizations of the external particles times a universal function, A of STU, which is crossing symmetric. Okay? And this is the objects that we will apply all these properties. Okay? In general, this superamplitude is very complicated, right? Because you can consider scattering of dilatons, gravitons, axidilatons, anything. But nevertheless, it's given by a universal factor that contains all the kinematical dependence times a universal function which is crossing symmetric. And it's a scalar function. So it's what we like and where we can apply all this technology. It's still a function of 2 variables. 2 to 2 scattering in any dimension is a function of 2 variables. Okay. And now, how we say that this is gravity, all right? And we will input this by imposing these constraints that this function of A of STU, when expanded at low energy, it will behave as some constant times 1 over STU alpha L Planck to the 6 plus dot dot dot. Okay? So this is an assumption. So this is just a constant, which is dimension full. Okay? Planck is the mass scale that we have when we scatter gravitons and there is nothing else. All right? 1 over STU term, it's fun because it does not come from any diagram, right? You cannot think of it as an exchange of particle, right? That would give some pole. This is just 1 over STU. Okay? And the trick is that this function of ASTU, it's not really a scattering amplitude. Because of this R to the 4 factor, right? Which is important. So, for instance, if we were to scatter axidilatons, all right? The amplitude for axidilaton, axi, will be given by a factor S to the 4 times this universal function, STU. This is what is really physical. And now if we multiply S to the 4 times 1 over STU, and we use momentum conservation, this is at low energy behaves like minus S square over T minus S square over U, plus dot dot dot, which really correspond to exchange of spin 2 particles in the T or U channel. Okay, so this is physical. But nevertheless, this is the crossing symmetric function. All right? So, all right. In other words, okay. So this is the setup. It's clear. So here now I'm scattering particles in the supermultiplet with some supersymmetry. And the only thing that, I mean, you can ask many questions if you want, but the only thing that you need to remember is that this function here contains a 1 over STU pole plus a constant plus higher order corrections. Very good question, yeah. Here I'm talking axidilaton, I'm thinking about the type 2b. Anyway, you can construct this S to the 4 time A even in type 2a, for instance, but it would not correspond to any physical scattering. Right? No, I'm just saying is that in type 2b, this would correspond to the physical scattering, right, of particles into supermultiplet.
Why it doesn't do that in that way? I mean, you see the dilaton there.
In type 2a, you need to, exactly, in type 2a, you just, you need to change a little bit this prefactor. And now this would, this is crossing symmetric factor, that would be a dilaton. Right, very good, very good. Right, because the axidilaton, for instance, can exchange, since it's charged, okay, right, can exchange graviton only in the T and U channel. Exactly. And the amplitude is, I mean, S24 times this function, it's not crossing symmetric. But for the dilaton, it would be crossing symmetric. Okay?
Sorry, Francis, on this.
Yeah.
Can I see the action of T2IT working on this thing? If I could change to get some T2IT working in the contract? So you have to modify the factor in that way. And I expect some...
So the factor is the same, both for type 2a and type 2b.
So you said that you have to modify them, I understood. So what you have to modify the factor in that way?
No, it depends on the massless spectrum. It's just that in type 2a, right. So you know that the massless spectrum contains dilatons, and if you want to extract a dilaton, you need to multiply by that factor. I'm not telling you how to do it. I'm just giving you an intuition about why it should be like that. Right? Okay, let me tell you a little bit about this term, for instance, to give you more intuition. This one over STU would come from R term in the effective Lagrangian, while this constant correction would come to R to the 4. Would be like an R to the 4 correction. Right? And that's why it's R to the 4, and you get this S to the 4. Right? Okay. So now this is about low energy, but what do we know? So this is actually general. All this low energy expansion depends on the fact that you have maximal supersymmetry, you are in 10 dimensions. But what happens, for instance, in string theory, right? So in string theory, this alpha correction, which is related to the R to the 4, can be computed both in type 2A and in type 2B. So for instance, let me write it in type 2B. It will be given by 1 over 64 times an Eisenstein series, right, which will depend on tau tau bar, which are the complexified couplings, all right? And actually, beautifully, it turns out that this function is bounded by a number which is roughly something like this. So in string theory, this alpha, it takes any value, but hits a lower bound, which is given by this number. And in type 2A, there is a very similar number, because the difference between the type 2A and the type 2B, it's just that in type 2B, you have, so in type 2A, so let me just say this. In type 2A, this alpha would receive 3 level plus 1 loop contribution, and that's so you can compute it because it's 1 loop exact, all right? And I'm introducing this G string because in string theory it's different from just low energy supergraduate, because we have also the string length. So we have an additional parameters, okay, with which you can define the string coupling, right? So as a function of string coupling, this alpha 2A can be computed. It's 1 loop exact. Okay, it stops here at 1 loop. Yeah. Yeah. Exactly. In type 2, yeah, in type 2A, what you have is that these first 2 terms plus a sum of the infinite d instanton contributions in type 2B that you don't have in type 2A. Exactly. So the difference between these 2 functions, it's just a sum of infinite instanton contribution that actually happens to be very small, because the difference, so at least for the minimum value of this alpha 2A, the difference is very small because the minimum would be like something like this, 0.14 roughly, for both type 2A, type 2B. Very, very good, yeah. So, very good. So this is related to unitarity in the sense that it turns out that both for type 2A or type 2B, if you construct this combination, okay, if you construct it anyway, this is the combination that enters into the unitarity. So unitarity for the supermultiplets just can be imposed on this combination. And if you want another intuition, is that this comes from what is called the duplication formula. It comes from this formula that basically if you sum over the 2-particle state, this R to the 4, so if you construct this tensor R to the 4 with index 1, 2 to any 2-point, any 2-particle state with R to the 4 that goes to some other polarization, right? This just gives S to the 4 times R to the 4 with this polarization. And that's why, since there is this duplication formula, this implies that unitarity, you need to impose it for this component. Even if it's, you know, in type 2B would be physical, in type 2A would be not. Yeah. 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 Yeah.
But the issues there was always the fact that you are doing something in field theory, but this field theory is highly non-normalized.
Right.
And then there is always some UV coefficient that you have to fix by hand, maybe with that theory.
Yeah, exactly.
So is there an issue like that in your...
Actually, no. There is no such an issue because Because as I will write in a moment, our ansatz is a non-perturbative ansatz for the scattering amplitude. That if you expand it at low energy, will contain this alpha, right? But this function is UV completed. The theory is not normalizable, but that's from the Lagrangian point of view. So I'm assuming there is a UV completion. Okay, and that this UV completion has this expansion. Exactly. Exactly, but thanks for the question. All right? So we have this situation that we have some string theory prediction from this alpha. All right? And what we want to do is that we want to minimize alpha in the generic space of scattering amplitudes. Okay, so this can be the scattering amplitude of any theory that is compatible with supersymmetry in 10 dimensions. It must not be string theory. We can just minimize it. Yeah. Right. Right. So the point is that the amplitude depends on this universal function. So this is the function that you care about. And this function is crossing symmetric. Right? Then you can multiply this function by different prefactors and get different processes. And the question that you need to ask is that, okay, this function is crossing symmetric, that's it. There is nothing else to say. The point is that how do I impose unitarity? And the way you impose unitarity is to construct this combination and imposing unitarity on this combination as to the 4 times A. Right. It's it's the way how is this A is defined, right? I define this prefactor R to the 4 such that this A is crossing symmetric. It's
maybe for the fact that the outgoing and ingoing states are different, so you cannot expect maybe that looking at the diagram from the top instead of from the left. The argument that justifies crossing symmetry that you reverse basically, you rotate the arrow of time, so maybe if you have axion, beta plus beta, you do not expect it to be the same.
Right. If you look at their processes, yes. Right.
What fixes the alpha? So how do you compute them?
This alpha actually, so there is a beautiful paper by I think Michael Green, Tsong-Kao Wen, well, a recent paper at least, but this was done before by Michael Green also, where they're using supersymmetry, they can derive differential equations that gives you this function. But the point is that to solve this differential equation, you need some boundary conditions. And the boundary conditions are given by string theory. So somehow low energy supergravity can tell you what is the differential equation that this function must satisfy, but does not tell you the boundary conditions. That you need string theory. Right? You need the fact that, for instance, you need the SL2Z invariance of the UV theory. And that's what fixes then this number also, which is not inputted to begin with into the bootstrap. That's not something that was inputted. Okay? So since time is up, I will just summarize here what we do numerically. And since it's just a number, I don't have any beautiful plot to show, because it's one, it's a line, right? Excluded allowed. So I can just avoid it. Right? So let me summarize. All right? So what we do, we have this function of AOSTU, which is crossing symmetric, that we write down with some ansatz. All right? So these ansatz take care of crossing plus analyticity. And then we do impose unitarity by constructing T, but multiplying by this S to the 4 factor, which is supersymmetry, right? Supersymmetry tells us to do. And we project this function into partial wave to construct partial waves projecting T. So we integrate t with the PL, right? So S and t, this will be a function of t. And we construct what were the partial waves. And afterwards, we impose unitarity. We impose the fact that 2 times the imaginary part of FL must be greater or equal than the absolute value of FL square for any L for any S. And this is done numerically. All right? And then the last thing that we impose, of course, is that this function A of S and T, which is a generic function, when we expand it for small s, for instance, it will behave like 1 over S2 plus alpha, where here I set to do the numerics L Planck equals to 1, plus dot dot dot. And in dot dot dots, there are all the UV completion. Right? So this is what we do. This is an optimization problem. And the result that we get is, well, yeah, in the dot dot dots can be anything. For instance, there, yes, actually there are. For instance, right, includes everything. Now you see, we are imposing this condition which is weaker than unitarity, right? So we are, this would be equal FL square plus multi-particle contributions. We are only imposing the inequality, right? So we are not telling how much particle production there is. It's just fixed by the numerics. Okay, so let me keep this alpha here. Right. So what we get is the following. Is this visible? No, not at all. And this is not, yeah, this is visible. Right? Okay. So I will do, okay. So what we do is that we minimize alpha. All right, so the minimization, minimize alpha. This is the problem. So we minimize that constant. And numerically, what we get is that we minimize, we go down, down, and down as we improve our ansatz, and we span on this basis of functions. As Lucia was saying, in 2 dimensions, we have some discretization for this basis of function, we span it, right? So we can go down, 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 minimizing alpha. At some point, we converge and we hit some boundary, right? And with some error bars, what we get is that alpha numerical must be equal than 0.13 plus minus 0.01. Which is, well, might be a coincidence, I don't know, but it's very compatible with what string theory predicts, for instance. All right? Okay. Now, what is this red line below? This red line below, it's related to these exclusion arguments. Okay. Which actually in this case is very simple, because another way to write down alpha, okay, is just that alpha is equal to, well, some factor times the imaginary part of t, okay, for t equal to 0, divided by s to the 5, okay? And the forward amplitude is positive by unitarity. So alpha is positive. So all the negative values are excluded. And this is a very simple dual argument to say that alpha negative is excluded. That's what we call the desert. While this is the garden. Right? Yeah. But, yeah, it's a little bit different. This is a physical swamp, right? Because between the garden and the desert, there is actually a swamp. So this is really physical. Right? So this is, we don't know. All right? And what we are trying to do now, and I'll stop here, that I don't have time to say, but what we are trying to do now is to fill this, try to fill this swamp, and really see if string theory realize all the possible UV completions of 10-dimensional supergravity or not. One spoiler is that actually doing better numerics with some different methods, we are finding that the minimum of alpha in the space of theories It's something more like 0.12, which is compatible with our previous bounds, but we have like more precise statement. So it means that the string theory is very close, but not actually the boundary, which is good, because what I told you is that in higher dimensions you must have particle production. And here I'm not imposing particle production, right? So in principle I could span also the space of theories that are not physical, right? So we do expect that if we impose particle production, and in particular we do expect that for graviton scattering you can produce black holes, and that will give you a huge inelasticity, okay? So that will have a huge effect. We have room now to increase this bound and really limit string theory. So if it were really the boundary, it would be dangerous, because imposing more constraints, we could exclude it. But now, being close, but a little bit below, we are in a better room for improvement. Okay? So I will stop here.
So let's start the discussion session.
So thanks, Andrea. Very nice. So first, I don't understand how to interpret this, the numerical value of the alpha, because we said that in the type 2b, for instance, you have alpha should be a function of your tau.
Right.
So what does it mean having a numerical value for alpha? Tau is a modulus. It can be anything, no?
Right. So for us, alpha doesn't know any, I mean, right? Yeah. It can vary arbitrarily, right? But what we are saying is that alpha can take any value up to 0.14. This is compatible with the fact that in string theory you have this tau, so this alpha you can move it around.
So is the bound for alpha then the same thing that the imaginary part of tau is greater than 0? Because
you mean where is it realized?
Yes.
Okay. I mean, yeah, right. So in string theory, so let me plot it in type 2b, exactly, right? So you have the fundamental domain,
okay,
right? And the nice thing is that, okay, there is like this point, tau equals I, and tau equals e to the I pi over 3. And actually, the minimum is realized that the tau equals e to the I pi over 3.
Okay, good. This is
the question. Which is a strongly coupled string theory.
Yeah.
Right? It's a strongly coupled string theory.
No, just a question. So alpha in type 2b, does it depend also on the Euler characteristic of the compactification manifold?
Oh, here I'm not compactifying anything. I mean 10-dimensional flat space.
Okay,
yeah.
So no, never mind.
Of course, if you compactify, you have many more modulus. So this alpha, right, can even take other values. So that's a good question. Actually, go to lower dimension and see what.
Would it be possible, in principle, to run a similar program in lower dimension and bound
yes.
the chi? Like I have in mind the alpha prime correction in type 2b compactification to 4D, for example.
Sorry?
I have in mind the alpha prime correction, the BBHL term, for example, type 2b on Calabi to 4 dimension.
Ah, I see. All the way down to 4 dimensions.
Yes.
Yeah. Yeah, 4 dimensions is this issue that we have infrared singular, so we cannot really go to 4 dimensions. So we need to, do it a little bit smoother, going to 8, 7, 6, 5. Right. I mean, we are actively working on these issues, as many people are working on the same issues, right? For instance, yeah.
What about 11?
Very good question. In 11 dimensions, this alpha is fixed, right? Because there is no moduli space. It's fixed in M theory. And we are running numerics there, but I still don't have results. But that's our next step, what we want to do.
But in that case, there is no scalar. I mean, how do you do?
The duplication formula still holds in 11 dimensions. So the super amplitude is still given by this r to the 4 factor times the scalar function, which is crossing symmetric. Yeah, okay. So, it's maximal supersymmetry. So maximal supersymmetry, it really gives this simplification.
So the original simplification is more maximal supersymmetry than the presence of a scalar.
Exactly. It's really maximal supersymmetry that helps you doing this. Yeah.
So maybe I don't remember very well, but I thought there were results in 9D though, in one dimension less, right?
Right. 9D, yes. In 9D, right, because in 9D you can compactify, and then by T-duality you can relate type 2A and type 2B, right? So in 9D, that's another thing that we want to do, but I mean, these are numerics are pretty heavy, so we do one thing at a time. It's like one step at a time, but in 9 dimensions, the dream is really to go to, okay, so maybe there is something I can okay, first the questions.
We come with the zoology question. I understand that it's maximal supersymmetry. In the case of heterotic, would you expect that the lower is higher? Do you have any expectations for like 1,0 or something like that?
Oh, that's a good question. Something we would like to look at some point, but I don't know. I haven't studied the literature yet.
You're doing that's really great anyway.
Yeah, so. There you should consider like gauge bosons also, so it's a little bit trickier, but yeah.
Okay.
Right.
So you said this alpha is the R to the 4 operator,
it's related
right?
to R to the 4, yeah.
So this sounds a bit similar to this like work on positivity bounds in effective field theory.
Right.
And in that context, they typically find two-sided bounds as well.
Right.
So I mean, when you say, so now you don't have any upper bound, are you sure of that, or is that something
Maybe
that should
amazing question, yeah. No, those bounds are for weakly coupled theories. So those two-sided bounds are for weakly coupled theories. But what we do is really we explore the whole theory space. And actually you see their bounds, I mean you see positive, you just hit alpha equal to 0. To get a non-trivial bounds, you really need to input the information that you are exchanging graviton, that there is some real exchange of spin to particles. And that, using unitarity, gives you bounds on this alpha. Right? Now, there is a physical meaning, actually, for this alpha going to infinity, because this alpha going to infinity corresponds to perturbative string theory. If we measure in units of L-Planck, perturbative string theory would have an alpha that is very big, which means that the effective field theory with the cutoff at the Planck scale becomes very unnatural. Because in perturbative string theory we have string length, so we have the massive states that become very light compared to L-Planck, right? So it becomes very unnatural, and that's why this Wilson coefficient explodes in units of L-Planck. So to put a two-sided bound, you need to consider only natural theory, and that's not a very, that's a perturbative statement. We don't know how to phrase it in a non-perturbative way, this statement.
So you're saying these bounds say more about the regime of the theory that you're looking at, in a way, like the two-sided bounds.
Yeah, it's about, if you have a weakly coupled theory up to some scale, then you can stop here. Then if you move the scale, you can stop somewhere else. But it's, up to you. Where is the scale where you want your theory to be natural? That would be the physical interpretation.
Can I ask?
Yeah,
yeah. This is speculative. So is there room for, since you are not using doing what you're doing,
yeah.
Is there any room for a possible theory type 2B or type 2A supergravity? Or
very good.
It can be inside that, yeah.
Right. So actually, this spoiler result would suggest that there is room, right? Because string theory starts here, this starts a little bit low. But you see, there is something that I haven't told you here because of time, but when we optimize, when we minimize alpha, this optimization fixes also the amplitude. And once we have the amplitude, we can look at the spectrum of resonances. As Lucia was saying, that they were looking at spectrum of resonance in 2 dimensions. And if we look at the spectrum of resonances for the amplitude that saturates our bound, right? It contains actually infinite resonances with the mass square here. This is J with a curve edge trajectory. So we get infinite resonances with the increasing spin. It's curved because it's non-perturbative. It's not perturbative string theory. All the masses are at L-Planck scale because the theory is natural. and it looks stringy.
Yeah,
so, you know, if it was not stringy, okay. But it looks stringy. So.
So one thing. So you are imposing unitarity only on the axi-dilaton component, or also on the other ones?
Sorry?
But what if you impose unitarity also on many other components?
Oh, they would be redundant conditions.
Ah, okay, they will all be redundant.
You know, it's related to the fact that, you know, there is maximal supersymmetry. So the dynamics really depends on one single function. So once you constrain that single function, that's it.
It doesn't buy you anything, okay.
So if you don't have maximal supersymmetry, what happens? That you have, you have different amplitudes for different delicities, right? And then for each process, you have different functions. And okay, that's what, right? And then you need to impose different unitarity conditions for the different processes because you have more components.
Is there any other question? Comments? Well, I guess we can thank Andrea again for the nice talk.